This is a walkthrough of Problem 2 on Exam 1 of Module 9 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 2, a rectangular wire frame, length 20 centimeters, height 10 centimeters, has a resistance of 0.01 ohms moving horizontally at a speed of 10 centimeters every second to the right towards this magnetic field region. It's going to continue at constant speed. It starts at 20 centimeters away from the region. The magnetic field in the box is 250 millitesla into the page. What is the magnitude and direction of the current in the loop at 1 second, 3 seconds, 5 seconds, and 7 seconds? The speed is 10 centimeters per second. It's going to take 2 seconds for this edge to reach the field. You should read this problem a few times, understand what's going on. This field is 40 centimeters wide, going 10 centimeters per second. You should read it again. I'll wait if you want to pause the video, just to make sure you wrap your head around what's going on. The question is for the current in the loop. There's only going to be a current in the loop when the flux through the loop is changing. When the flux is changing, there's going to be an EMF in the loop, and this voltage will produce a current around the loop, and that current is going to oppose the change in flux. So let's start by drawing the position of the loop at each of the 4 times. So here's where it starts. We want to know where it is at 1 second, 3 seconds, 5 seconds, and 7 seconds. It's going 10 centimeters every second. At 1 second, it's going to be out of the loop. It moved 10 centimeters. It's now 10 centimeters away from the magnetic field region. At 3 seconds, it's going to be halfway in and halfway out. At 5 seconds, it's going to be in the middle of the field. At 7 seconds, it's also halfway in and halfway out. So from this, we should be able to see that the field, the EMF in the loop at 1 second and 5 seconds is 0, because the flux is not changing. The flux is only changing at 3 seconds and 7 seconds. So we have half the problem done already. There's no current at 1 second and there's no current at 5 seconds because the flux through the loop is not changing. Remember, it doesn't matter what the flux is. What matters is the rate of change. The flux at 1 second is certainly different from the flux at 5 seconds, but the rate of change is the same, and that rate of change is 0. So we have to focus on 3 seconds and 7 seconds. What is the rate of the change of the magnetic flux at 3 seconds? Let's take a closer look. Let's zoom in. The leading edge of the frame starts 20 centimeters away, and it moves at 10 centimeters per second. It takes 2 seconds for that leading edge to hit the field. 1 second later, it's going to be halfway in. Here's what it looks like every 1/10 of a second. So there's 2 seconds after it started. It's going to come into the field. 2.1, it's 1 centimeter in. 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9, and 3. We want to know the rate of change of the area that's in the field. The magnetic flux, the field is constant, so dB dt is 0. The reason why the flux is changing is not because the magnetic field's changing, it's because the area of the loop in the field is changing. Let's take an even closer look because we really want to understand how to calculate dA dt. We're going to add a 1 centimeter grid to the frame. The frame is 20 centimeters by 10 centimeters, which is 200 square centimeters, 10 by 20 square centimeters. And let's take a snapshot of it every 1/10 of a second. If it's going 10 centimeters in 1 second, it's going 1 centimeter in a 1/10 of a second. So how much area of the loop enters the field each 1/10 of a second? If that's 2.0 seconds, the speed, 1 centimeter per 1/10 of a second, that's 2.1. So 10 square centimeters entered the field. These 10 square centimeters right here. 10 square centimeters go in a 1/10 of a second, which is a rate of 100 square centimeters every second. At 2.2 seconds, it looks like that. Every tenth of a second, 10 square centimeters enter the field. At 3 seconds, there's 100 in there. It's halfway in. There it is. So from 2 to 3 seconds, 100 square centimeters, this area right here entered the field, and it took 1 second. So the rate of change, no matter how you calculate it, of the area in the field is 100 square centimeters every second. Okay, now we can do it. The EMF is the rate of change of the magnetic flux. The rate of change of the flux is dBA dt. B is constant here. dA dt we know, we just calculated 100 square centimeters every second. The B field's constant, 250 millitesla. Converting to SI units to get volts, we have 250 times 2.5 times 10 to the minus 3 volts. The resistance of the wire is 0.01 ohms. That's given, so now we can calculate the current. To get the current in the loop at 3 seconds, we know what the rate of change of the area is. We use V is equal to IR, the EMF, 2.5 times 10 to the minus 3 volts. We can calculate the current. It's 250 milliamps. But we have to do the direction as well. Let's think about the direction. When the loop is entering the field, the flux is increasing into the page. The induced current is going to produce a magnetic field that opposes this change. So it's going to make a field out of the page. The current in the loop must be counterclockwise to induce a current, to induce a magnetic field out of the page inside the loop. So the current's going to the right in the bottom. If we put our thumb to the right and curl our fingers around, the magnetic field from the loop is coming out of the page, and that's the way it has to be. When the loop is exiting the field, the magnitude of the current is the same because the rate of change of the area is the same. So at 7 seconds, the rate of change of the area is exactly the same. The current, the magnitude of the current is going to be exactly the same, but the direction is going to be different. It's going to be opposite because now it's leaving the field. It's losing flux. When it's leaving the field at 7 seconds, the current's going to be clockwise. So now we have the answers. At 1 second, there's no current in the loop because there's no change in magnetic flux. At 3 seconds, it's 250 milliamps counterclockwise. At 5 seconds, it's 0. And at 7 seconds, it's also 250 milliamps, but it's clockwise. That's problem 2.